Vamos con la siguiente mesa que va a moderar Eugenio Trillo, es CEO en Siemens Energy, es director y cofundador de esta empresa andaluza. Además, también cofundó el clúster andaluz del hidrógeno. Lidera programas formativos de hidrógeno en la Escuela de Organización Industrial. Es premio ingeniero joven andaluz del Colegio Oficial de Ingenieros Industriales y actualmente está realizando un doctorado sobre compresión electroquímica de hidrógeno. Él va a moderar a 4 ponentes para hablar de las tecnologías emergentes en hidrógeno verde, a Olga Monclús, que es gerente de ventas técnicas de sistemas de energía sostenibles en Siemens Energy. Ella es ingeniera química, con más de 20 años de experiencia en el desarrollo de negocios, áreas de ventas dentro de los sectores químico y energético. Ha trabajado para importantes empresas internacionales, en España y en Francia. Líder senior de ventas en proyectos de España, América Latina y Oriente Medio. Junto a ella estará Robert Shelton, presidente y CEO de H2V Safety Pipe. Ha supervisado con éxito grandes iniciativas público-privadas y es el inventor o coinventor de 17 patentes, más de una década de experiencia en tecnologías de transporte para hidrógeno gaseoso y líquido. Francisca Segura, presidenta de la Cátedra H2 Gabitel, doctora en Ingeniería con la calificación cum laude, Premio Extraordinario de Doctorado y Premio AIQB. Coautora de más de 50 artículos, ha cotutorizado 4 tesis doctorales, todas calificadas también con cum laude. Más de 20 proyectos de investigación a nivel europeo, nacional y económico han contado con su participación y terminamos con Delia Muñoz, que es responsable de proyectos de H2B2 Labs, donde está al frente de proyectos de I+D. Ingeniera industrial con más de 15 años de experiencia en proyectos basados en tecnologías de hidrógeno y pilas de combustible, así como gestión de riesgos, contratos y órdenes de compra. Bienvenidos. Muchas gracias.
Gracias. ¿Qué tal? ¿Nos escucháis? Está la sala un poco vacía, yo la he visto más llenita antes, ¿eh? Aquí estáis los que sois más estudiosos. Bueno, esta charla la vamos a hacer en inglés, ¿vale? Así que, bueno, yo creo que la mayor parte de nosotros somos personas españolas hablando inglés, eso va a ser más fácil, ¿vale? Con Robert, él lo va a hacer genial, ¿vale? Bueno. Today we are gonna speak. I'm gonna translate my draft from Spanish to English, so I'm gonna be slow, no problem. And we are gonna speak about starting technology. We say in Spanish, Emergentes. And here we are gonna do a loop between production. Some different types of hydrogen production, and then we are going to move to distribution, and finally we are going to be talking about maintenance, okay, with Paki. We are a little bit mixed, but it doesn't matter. You're gonna see, okay? So one thing I want to share with you, I was talking with my colleague Vicente. Vicente will be, I hope so, about green hydrogen, renewable hydrogen has to fight against another molecule that has been doing the work during thousands of years. So when you take petrol, when you take natural gas, thermodynamically speaking, someone did the job. And something very hard today with green hydrogen, electrolytic hydrogen, is that we have to break the molecule in that moment, and this is hard. Most of you have heard about green hydrogen is too expensive. Well, the molecule that is you are generating, it's very energetic. So this is thermodynamics, right? And we are fighting against something that it took a lot of years to do it. So now we are going to see how research and development can, let's say, close the gap between this, as we say in Spanish, dinosaur juice, and we go to the green hydrogen and the white hydrogen, and as we were talking before. So I'm going to start with Olga, then Delia, then we're going to move to Robert, and then with Paki. So, Olga, talk to us about the technology you have in Siemens Energy, and what is the new thing you are doing there.
Thank you, Eugenio. First of all, it's a pleasure to be here, to be with my colleagues in this panel, and I hope that we can bring a good discussion to this conference. So to your question about Siemens Energy electrolysis technology, first of all, I would like to say that in Siemens Energy, we have a long experience background developing electrolysis or different technologies around PEM membranes, starting with fuel cells, and later with electrolysis, that is the main product that we are commercializing today. We started 30 years ago, as I said, with fuel cells, and then we continue with the development on the electrolysis side with the first product in 2011, a small one, the size of kilowatts. And we are today with the LISER P300, sorry, on a scale for a single array of 17.5 megawatt. And this is the main product and the only product that we have at this moment in the market. But obviously, as every technology company or other OEMs, we are continuing developing. And then the most important that I wanted to bring today here is about why PEM atmospheric, okay? Because this is the main differentiator, I would say, because Siemens Energy is the only one that has this technology in the market, PEM atmospheric. And basically, the point is that in Siemens Energy, we have developed a ROS system and prioritizing the safety and the reliability of the system in order, as Manuel said before, to de-risk our technology. Because we think and we believe that this is the way to proceed for a larger scale development of the hydrogen economy. And then what I wanted to say about this, the main point about the atmospheric PEM, is that safety and reliability in this case are together. Why? Because PEM atmospheric reduce the crossover of hydrogen from the cathode side to the anode side. And this can ensure that the life of the membrane can be as expected or as warranted. And I'm saying this because before, the previous system that we have in Siemens Energy, S200, was working at much higher pressures. And then at that moment, Siemens decided that it was not the right product or the right technology that we wanted to bring into the market for this challenge of development. And then that's it. We realized that the crossover from the hydrogen to the oxygen side, could have an issue, and as well is affecting the durability of the life of the membrane itself. Because you need to add recombination catalyst in order to ensure that the hydrogen that crosses over through the membrane recombines into water. But this is a hydrogen production loss. And at the end, it's affecting as well the stability of the membrane itself. So I can continue extending myself about other advantages of our technology, but we don't have time. And only to say that as emerging technologies that you mentioned, we can see that I think that every technology company is continue developing or trying to innovate on the systems, on the membranes itself, that is the core of the system itself. And we see the AM, that it's as a promising technology, could be much more cost-effective, considering that there's no precious metals in the catalyst. Yeah. But still under a TRL of 4, I would say.
We are going to see with Delia.
So that's it. This is what I can bring at this moment about our technology and how I see the next step.
And now you are going to share with us some experimental conclusion that you have. So we are going to follow with Delia. Delia, she has give a short news. AM, SOEC, those technologies we see like so we have everyone should know about alkaline and PEM. And normally, when you compare, it's more or less the same. But after that, you have solid oxide, anionic. What are you doing in H2 in those technologies, and how do you see those technologies to go to the, let's say, the industrial step?
Okay, so, well, as we all know, those are the emerging technologies, PEM and alkaline, very mature, AEM and solid oxide in a less mature state, but more mature, it's months, because there is a lot of investment in the development of those technologies. At H2V2, we have, I think that all the projects that we had dedicated to R&D, that are like 10 or 12 projects, and we are a small company, almost all of them are dedicated to those technologies, from the stack level to the system level. And well, there is a lot of projects, national, European. So I think in the not so long term, in the short term, they will be maybe not competing at the same level as PEM and alkaline, but they will be getting closer very fast. So regarding the challenges for that to happen, in the case of AEM, well, the efficiencies are similar to PEM. The cost will be lower because it doesn't have precious metals, so that's the key of the AEM technology. But the challenge is in the materials for the membrane, for the electrodes, to be able to work in an alkaline environment. This is where more investigation is needed. The membranes can degrade faster. Polymers, but are working in an alkaline environment, so can degrade faster than for PEM. And the electrodes can be, the corrosion can affect the electrodes, so it's also the problem, no? What we need to solve. So once all those projects that are now in R&D can give us the key to find the right materials for those electrodes and those membranes to have a longer lifetime, I think that would be when we will have commercial AEM electrolyzers. And in the case of solid oxide, well, we all know the temperature. We work at a high temperature. That is the advantage, because we have a high efficiency when we have that waste heat and we can use it. But it's also the disadvantage, because all the materials need to work and have a durability to be able to be compared with other technologies, working at 800, 900 degrees. So there is also a lot of investigation there. We are working, as I said, in a lot of projects in that area. And well, solid oxide electrolyzer, I think, are more mature even than AEM. But we need to work on that, and the integration, not only in the stack, in the ceramics, to be able to support the temperature changes, but also the integration, the heat management is complicated, but I think we are close to getting closer to the more mature technologies.
Thank you. Thank you so much. So as you can see, we are talking about production. We are with, let's say, the more mature technology, emerging technology. Now, once we have generated the molecule, we have to send the molecule from point A to point B. So there is where Robert and the company he's managing comes to action. So H2C safety pipe. Talk to us more about the technology, and then we will go deep in other points.
Great. So first I want to thank all of this panelists for speaking in English.
You're welcome.
Because that was not their native language, and I don't think they prepared to speak in English. So thank you very much, all of you. And I'd like to thank all of you because this is my first trip to Andalusia and to Huelva. I come from the United States, where we're going through some challenges with hydrogen and some questions about what will become of hydrogen. I also come from California, which is very similar in its climate to what I saw outside this afternoon. And my hope is that we're creating a bridge between what we're doing in California and what you're doing in Andalusia. Because I think when I see the size of this event, when I see the interest in hydrogen here, we have that same fascination, interest, and passion for decarbonization and for the benefits of hydrogen, not just for ourselves, but for our grandchildren and our grandchildren's grandchildren.
That's right.
And so to speak to the subject of the business that we are in, we focused on the potential for connecting between where hydrogen is the least expensive to produce and where green hydrogen is most needed, where clean energy is most needed. And if you don't do that safely and economically, then neither of those two ends of the barbell have a bar to connect them. And so our objectives as we started were economics. We needed to drive down the cost and safety. And the recognition of safety was that hydrogen leaks. Hydrogen leaks, it's the smallest molecule. It leaks through anything. It leaks through steel, leaks through polymer, it leaks through cracks, it embrittles, it corrodes. It's not a favorable molecule to hold in place. And so you mentioned safety. Thank you. I wouldn't have understood that if it was in Spanish, but thank you for mentioning it. We focused on safety, and we do that through containing the hydrogen transport pipe inside of an outer pipe that we call a safety pipe, therefore our name, H2C safety pipe. And in between the inner pipe that contains high pressure hydrogen, gaseous, and the outer pipe, which is containing anything that leaks out of that inner pipe, we have a sweet gas that is nitrogen. And any time that the volume of hydrogen reaches some percentage, 25% of the lower flammability level, which would be around 10,000 parts per million, then the sweep gas is able to carry that hydrogen out of the system and remove it. And we're removing it before it enters the atmosphere, because there's a major concern in California and I think also in Europe of the hydrogen entering the troposphere, the atmosphere, and becoming it's not a greenhouse gas, but it interacts with the components of the troposphere that remove the greenhouse gases. And so the environmentalists are terribly concerned if the hydrogen leaks. And so we're able to protect the safety, protect the leakage, and drive down the cost, ergo our technology.
Thank you. I think that this week or 1 week ago, it was an announcement about connecting Huelva and Algeciras with a pipe. So guys, constructing pipes, please talk with Robert. You have a job to do. So Paki, we go with you. So I would like you to talk about which strategy are you following to reduce the cost in the electrolysis plants?
Yeah. Now we are more or less paying about 1,000 euro by kilowatt of electrolysis for a machine that has a lifetime around, in the best case, around 60,000, 80,000 hours of operating. So this involves to sell hydrogen, low emission hydrogen, at a cost of about 3 2 or 3 times more expensive than hydrogen produced by conventional methods like reforming, methanol reforming. So we can sell hydrogen, but maybe nobody buy this hydrogen so expensive. So the strategy to identify it to act are five points. One is entering into the stack design to increase the module of the stack. Now we are talking about a square meter for alkaline, a square decimeter in pen, and a square centimeter in AM. So we need to increase the size of the cell and in the size of the stack. The second point is the automatization. If we examine the stack and we build the balance of plant by manual in a handmade, it involves cost and delay. The process lasts more than with an automatization process. The third point is the material. Yet some colleagues are talking about the material. Now the prevision is the production, the extraction of iridium or platinum to cover about 7 gigawatt of electrolysis. And if the goal is to arrive until 100 gigawatt, where are the material? The last points are efficiency to match efficiency and flexibility. We know that electrolyzer needs a power supply in the middle of the connection, in the middle between the panel and the electrolyzer. We need a power supply. The efficiency curve of a power station is increasing until to achieve to the nominal power. So we need to decide if we want that electrolyzer operate only in a narrow window with high efficiency, or increase the narrow but working at lower efficiency. And the last point is the learning curve. What we are learning about the product, the equipment we are manufacturing. Now, some of the companies offer the monitoring as an additional service, but is everybody ready or want to pay for this additional service? We need to know not only the process, but after the implementation, we need to know all the operating life of the machine. So it's necessary to monitor the plant and to have a logging of the operation, of all the operation hours. They are the 5 points.
As you can see, University of Huelva has been working on hydrogen for a very, very long time. I would say probably that I was like a kid and they were there. I see over there another professor of the university, so talk to them, because as you can see, they know a lot of hydrogen, not only research, operational, and when you get your hands dirty. So you have people here to work with. Okay. So we have done the first round. We are gonna start with the second one. I'm gonna start again with you, Olga. So I will tell you that we are the table that is short in the time. So don't worry. The beer is over there. And so something that I would like to ask you is about the operational experience your technology have, because something that we see everyone here with some hours working on hydrogen is that there is a lot of PowerPoint, but you can tell us about real experience. So
Sure,
go
sure.
ahead.
Siemens Energy, we have a good experience, and we are starting to scale up our technology. I guess that Manuel already mentioned about the last news with NEW, that we are starting to, as I said, to scale up our technology. And first of all, I would like to say that it's important for these technologies in order to prove the technology itself. And it's not only in a lab validation or demo validation scale, but you need to reach megawatt, 1 digit, and then to scale up and to prove not only the technology of the electrolyzer itself, but as well the integration at a plant level, and this is very important. So, as I said, we have a long background in the electrolysis in Siemens Energy, maybe more than, I would say, 250,000 hours in operation for the smaller systems below, I would say, with the module of the array of, or the module itself of around 1 megawatt. This is a long experience, but now with our current product, we have, let's say, one of the references that we are more proud, and is the one developed with Air Liquide, that is our partner. We have a strong partnership with Air Liquide, that with his experience in the hydrogen operation and with Siemens Energy, innovation in technology, it's very important. It's a good combination. And this is, Air Liquide was starting, it's around, let's say, it's one array of our ELYSER P300, and it started almost 2 years in operation now. And we have learned a lot, not only about our technology, but as well about the system itself and the erection and the commissioning phases as well. It's used, all these projects, to improve our internal execution for the next project, okay? And then so at this moment, the biggest reference that we have in operation is 20 megawatt, this one, but we are starting in commissioning of 2 other plants in Denmark and in Germany that will be by April, May this year, will start operation. First hydrogen production has started. They are under commissioning phase. So this is a good step to continue demonstrating our technology. And as Manuel said as well, we have biggest projects with Air Liquide in France. We are talking about 200 megawatt, 280 megawatt projects in Germany. So I expect that in Spain soon, we will start seeing this size of projects that are starting happening in Central Europe or in North Europe. And I hope that Siemens Energy can participate of this. And last to say, I would like to say that it's a learning curve about our technology, and we need data of these operational assets, okay, or plants, in order not only to improve the system itself and to can prove the reliability and the life of the membranes itself, but as well as lessons learned for cost improving and in order to be able to deploy this technology at a large scale.
Thank you. Thank you. We are short time, as you can see there. So talk to us about efficiency and emissions with AM and SOEC, please. So
for solid oxide, as I think we all know, efficiencies can be very high. Well, we are using the heat to promote the reaction. So if you have a waste heat that you can use, you need less electrical energy, so efficiency is high. It's high if you don't need to evaporate the water or anything like that. You already have that heat available. So we can reach like a 90% efficiency for a solid oxide electrolyzer. We all know green hydrogen as long as you use renewable energy. In the case of solid oxide, you need a stable electrical input. So it's not easy for direct coupling with solar energy or wind, but well, you have green hydrogen if you have a stable electricity, green electricity. So with those two requirements, you had a very high efficiency. In the case of AEM, efficiency is similar to PEM, and is cost is less cost than for PEM, as you don't need those precious metals, so it's also more sustainable. So in that sense, in both cases, in the terms of efficiency, they can compete and even overcome the more mature technologies. For solid oxide, we also need to work in the pressure because you have like atmosphere pressure at the outlet. So if you need to use more energy to compress the hydrogen, this is something that can penalize the whole efficiency. But those are issues that can be easily solved. So I don't think that efficiency could be a disadvantage in this case. It would be the opposite. So as soon as those technologies overcome the challenges that we were discussing previously, I think they can be at the same level or even higher than PEM and alkaline.
Thank you. Thank you. So Robert goes to the point. Applications and how much costs the pipe.
Okay, I'm going to give you more time. There is a session later this afternoon at 4 o'clock that Javier Jano is presenting on green hydrogen engineering and transportation, where he will go into detail. He has 20 minutes. I have one. So he will go into detail, but suffice to say, the cost is substantially reduced, and there are multiple applications. The ones that excite me the most are the ability to actually pull the pipe inside of existing pipes so that you get pure hydrogen coming through a former natural gas pipe. We think there's also ways that you can have hydrogen and natural gas coming through the same pipe without blending and therefore have better economics. So talk to Javier, come to Javier's session, talk to myself or my colleague Jerry Brown. Our great honor to be in relationship with Clantech Technology and Engineering. Please visit us.
If you have any doubt, you ask me to also, and I will send you to where he's telling to us, okay? Thank you, Robert, for your resume. Paki, let's go with the final point. So give us, please, some examples of tools you are really using right now in your research work.
Yes, from the research point of view, one of the different lines we are carrying on the university, at the university are one, defining a strategy to balance the degradation in electrolyzer. In case of a modular system made by different multiple stacks, it's key to identify if we want to degrade only one stack in favor of the rest, or we want to balance the degradation, and all the stacks are going to degrade in the similar way along the lifetime of the project. The second point, the second research line is the dynamic degradation. As we know, the manufacturer has one a certain amount of voltage by operating hour, but with the time, maybe this factor is changing. So the dynamic degradation is key, and even if we want to translate the degradation into a model like a digital twin, we need to know in real time the plan. So it's key to know the dynamic degradation. And the last point is the use of fuzzy system or artificial intelligence-based system to observe a sensor that going down or maybe failure, and with a neural network to act in case a sensor fails. So if the real sensor fails, maybe the neural network is being trained and deliver the output in case the sensor fails. So they are 3 examples of resource we are developing from the research point.
Thank you so much. Thank you guys. We are in the last minute, so I'm gonna close. Thank you guys for hearing us. I think that green hydrogen, we don't have time to talk about white hydrogen and all the types of hydrogen that we can use to produce cheaper hydrogen. But something that is important, and I would like you to hear that, is about research and development. Is the only way we can go from the expensive, let's say, hydrogen. If you want a small chat about what I think about that, come to the Lean Hydrogen stand and I will tell you something about that. But if we want to reduce the price of the hydrogen, the electrolytic hydrogen, we have to do research and development, and we will get it. If not, anyone is going to do it. So your choice. Bye. Thank you.